This video is a supplement to the application of vapor pressure in Lecture 2 of Topic 4. This problem is Exercise 1 given in Lecture Note 2. The process in this problem happens every day in industrial or commercial sites where they have tanks to store fuel or chemicals. In this problem, the chemical is toluene. When the tank is filled with a liquid chemical, upon consumption, the empty space on top of the liquid, which is here, is filled with air or nitrogen so that the pressure inside the tank stays the same, normally atmospheric pressure. When the tank is low and gets filled, the vapor on top is driven out through a vent pipe or duct by the liquid that replaces it. So the liquid is filled and the vapor is driven out. The vapor contains the chemical and it is a cause of air pollution. Since the tank is closed to prevent the vapor to escape, this vapor becomes saturated with the liquid that is in contact with it. Note that this is different from one component system we saw before, where water vapor was the saturated gas on top of liquid water. Here we have a mixture of air and the component which is toluene. So here we have air and toluene in equilibrium with toluene. To reduce the pollution, the vapor is led to a system that you see here in this problem, a compressor and a cooler, to recover some of the toluene chemical. The saturated vapor enters the compressor that raises the pressure of the vapor to P. As a result of rise in the pressure, we may have a mixture of vapor and liquid exiting the compressor. So here it is saturated, however it may have some liquid in that stream with it as well. In the cooler, the temperature is further reduced, causing more liquid to condense. The less concentrated but still saturated vapor exits the cooler that is allowed to escape to outside according to environmental standards and regulations. In this problem, 900 gallons of vapor, which is 1000 gallons minus 100 gallons, at 85 degrees Fahrenheit and 1 atmosphere, is forced out. In part A, we would like to know how much toluene is in this vapor that is escaping. We know the vapor is saturated, so the partial pressure of toluene in the gas mixture, which is air and toluene mixture, must be equal to the vapor pressure of toluene at 85 degrees Fahrenheit. In Antoine equation, temperature is in degrees Celsius. And also, the parameters A, B, and C are read from the table. And this equation, as the table says, is applicable within this range, and 85 degrees is well within this range. So we convert the temperature to degrees Celsius for Antoine equation and we plug in all the numbers to get the vapor pressure, and the vapor pressure of toluene at 85 degrees Celsius would be 36 millimeter of mercury. Having that vapor pressure, we know partial pressure of toluene in the mixture is the same as that. So having the partial pressure of toluene, we can get the mole fraction of the toluene in the mixture as partial pressure over total pressure. This total pressure is 1 atmosphere, and then we have the partial pressure from here. We will get the mole fraction of toluene. In order to get the mass, we can first get the moles of toluene in the vapor, and we know that the moles of toluene is mole fraction times total number of moles. in order to get this total number of moles, we may use ideal gas law. So here, as you see, we have used ideal gas law. We plug in the volume of 900 gallons and then the temperature of 85 degrees, and we will get the total moles of the air and toluene mixture as 0.3024. Once we have that, also we have the mole fraction of toluene. This will be the total number of moles of toluene. Once we multiply it by its molecular weight, we will get the mass of toluene as you see here. In part B, we want to recover 90% of toluene. In this part, we are looking for a temperature that we need to operate our cooler so that we achieve 90% recovery. So this temperature is the unknown in the problem, and it is a mass balance problem. We draw a flowchart for this problem. The feed stream, moles, and composition is known from the previous calculations. Let's number the outgoing streams as number 1 and number 2. Here we are gonna have 3 unknowns, 2 here and 1 there. We can write 2 balance equations since we have 2 components and 1 process specification related to 90% recovery. So degree of freedom is 0, and we can get Y1, the mole fraction of outgoing vapor at 5 atmosphere. We know Y1 would be equal to the partial pressure of toluene over the total pressure in this condition. The total pressure is 5 atmosphere. Having Y1, we can get the partial pressure of toluene. Once we have the partial pressure of toluene, we know this stream is saturated, so vapor pressure of toluene at this temperature, which we don't know, is equal to the partial pressure of toluene, which we know it already. Once we have this vapor pressure, we can solve Antoine equation for the temperature T, and we can answer the unknown to the problem.